Hello, I am Somnath Dasgupta. I teach in Jamia Millia Islamia, New Delhi. Today, we are going to talk about metamorphism of mafic, calcareous and ultramafic rocks. We will start with the mafic rocks, but before that, you should know very clearly what is the mineral composition of mafic rocks before metamorphism. By mafic rocks, I do not mean only the mafic igneous rocks, some mafic tuffs or some very unusual mafic metagravaceae are also included. Basically, they produce similar metamorphic mineral assemblages during metamorphism, so they can be clubbed together. But my focus is always on the more abundant rock type, that is the mafic igneous rocks, and you all know that mafic igneous rocks contain mainly calcic plagioclase, orthopyroxene, clinopyroxene without olivine before metamorphism. You can think of gabbro, dolerite, basalt or similar rocks which are now going to be subjected to metamorphism. One of the striking issues that appears during low grade metamorphism of mafic igneous rocks is the abundance of hydrous and carbonate minerals. Now, presence of hydrous minerals and carbonates obviously imply that there was some fluid influx during low grade metamorphism. The question is, from where did the fluids come? People have debated about the source of fluids, and since most of the mafic igneous rocks occur in the oceanic crust, they think that the oceanic water could be a possible source of those fluids. But let us not speculate about that. The fact is, in low grade conditions, low grade metamorphic conditions, these rocks contain a lot of hydrous and carbonate phases. Now, obviously, we will compare our results with metamorphism of pellitic rocks that we have described in a separate module. In figure 14.10, I have depicted a general table which shows the mineral assemblages in mafic igneous rocks in different metamorphic facies conditions. For comparison, I have also included at the bottom of that figure the zones, the Barrovian zones that are developed in the pellitic rocks. So, now you can see that the nature of mineral assemblages varies completely differently from those observed in pellitic rocks. This shows the importance of bulk composition on the appearance of different metamorphic minerals. If you scan through the list, you will see three very striking features. One is that plagioclase becomes calcic at higher grades of metamorphism, particularly in the amphibolite facies and higher grades. Then you will see that the amphibole is actinolite at lower grades of metamorphism and becomes hornblende at higher grades. Now, you may recall the difference between actinolite and hornblende. Actinolite is a non-aluminous amphibole, hornblende is an aluminous amphibole. So, naturally, I can summarize by saying that amphibole becomes aluminous with increasing grade of metamorphism of mafic igneous rocks. And thirdly, important thing to note is that the two pyroxenes, orthopyroxene and clinopyroxene, they appear at the highest grade of metamorphism in the granulite facies. These granulite facies metamorphosed igneous rocks, mafic igneous rocks are often referred to as mafic granulites or 2-pyroxene granulites because they contain 2 pyroxenes. Now, let us start with the metamorphism of mafic igneous rocks under the medium pressure facies series, just like what we did in case of the pellitic rocks. The medium pressure facies series in the chlorite zone and in the biotite zone in the pelites, so to say in the green schist facies, mafic igneous rocks are composed of chlorite, albite, actinolite, epidote, quartz with or without carbonates. So, that is why I said in lower grades you have hydrous minerals and carbonate minerals in mafic igneous rocks. Now, plagioclase is albite, almost nearly pure albite, that is to say it is not a calcic plagioclase, and epidote, actinolite, chlorite, all are green minerals, as a result of which this green schist facies metamorphosed mafic igneous rocks are dark green in color, and that is why they are often referred to as green stones. Now, you might have heard about green stones occurring in Archean cratons. These are nothing but green schist facies mafic igneous rocks. At the entry into the amphibolite facies, often we get a transitional facies which we call albite epidote amphibolite facies. Here what happens is that two important mineral changes occur. First is that amphibole becomes aluminous, and at a slightly higher temperature plagioclase becomes calcic. Now, what is the source of this calcium and aluminum? The source is possibly lying with chlorite and epidote. These are the two minerals which break down, and in the amphibolite facies then we have the minerals like hornblende, calcic plagioclase with or without garnet. Garnet may be present, may not be present. But what is important to note is that this rock itself is called amphibolite. So, the term amphibolite actually has double connotation. One connotation is the amphibolite facies that we described earlier, and a mafic igneous rock metamorphosed under amphibolite facies condition is also called an amphibolite. So, this is a rock amphibolite, and we often distinguish between two kinds of amphibolitic rocks. One is called orthoamphibolite and another paraamphibolite. Orthoamphibolite means the rock has been derived from an original igneous rock, and paraamphibolite means original protolith was some kind of very unusual marly sedimentary rocks, very unusual, but it is possible to have that. So, in the amphibolite facies, mafic igneous rocks are called amphibolites, and they contain hornblende and calcic plagioclase with or without garnet. Now, with entry into the granulite facies, this hornblende starts to break down and produces first clinopyroxene and then orthopyroxene. So, in the granulite facies we get the two pyroxenes coexisting with calcic plagioclase, and hence the name 2-pyroxene granulite. Now, if I increase the temperature further, then what happens is exactly the same as in pelitic rocks. Now, instead of micas, here hornblende breaks down and hornblende partially melts to produce 2-pyroxene with or without garnet assemblage, and a melt which is tonalitic in composition. So, this is not a granitic melt, what we got in case of pelitic rocks, here we get a tonalitic melt. Now, this melt can crystallize as enderbite or charnockite in Archean cratons. So, you see metamorphism of mafic igneous rocks are very well studied in greenstone belts and in ancient Archean cratons, and also we have some evidence from the younger orogenic belts as well. So, in figure 14.11, I have given a petrogenetic grid in which I have shown all possible mineral reactions in a mafic igneous rocks as a function of pressure and temperature. And you can see the sequence of mineral assemblages developed just as I described. They are reflected in a sequence of mineral reactions which are encountered one after another during progressive metamorphism. And you can see the orthopyroxene and clinopyroxene forming reactions on the right hand side. Now, in figure 14.12, I have given you a schematic diagram showing the mineral assemblages in mafic igneous rocks in the amphibolite, granulite and eclogite facies. You will note that hornblende plagioclase with or without garnet are the characteristic mineral assemblage in the amphibolite facies and the 2-pyroxene assemblages in the granulite facies. But there is every likelihood that hornblende continues at least partially into the granulite facies. And then you see that in the higher pressure region in the eclogite facies you do not have plagioclase. I will describe eclogite facies separately, but the important thing is to note a region just below the eclogite facies where you do not get any orthopyroxene. You get clinopyroxene, you get garnet, you get plagioclase, but no orthopyroxene. Now, this is a very narrow range of pressure temperature conditions where in mafic igneous rock orthopyroxene disappears and still plagioclase is present. So, I cannot call it an eclogite. So, what do I call this rock? This orthopyroxene free clinopyroxene, garnet, plagioclase rocks are called high pressure granulites or popularly as HP granulite. Now, more and more occurrences of HP granulites are now being reported from many parts of the world. So, this is the story about the Barrovian type metamorphism of mafic igneous rocks. We move on to the low pressure facies series. Here, the sequence of metamorphic facies is completely different. We have albite epidote hornfels facies giving way to hornblende hornfels facies, giving way to pyroxene hornfels facies, giving way to sanidinite facies at the highest temperature. So, it is completely different from the sequence what we get in medium pressure facies series. Now, there is not much difference in mineralogy, however, so it is easy to remember. The only thing that you need to remember is that garnet is less abundant in low pressure facies series. The most interesting story lies in the high pressure facies series metamorphism of mafic igneous rocks. Here, what you get is a completely a different sequence of metamorphic facies. You start with the geolite facies, where hydrated calcium aluminium silicates belonging to the geolite group and allied mineral groups are the abundant minerals in mafic igneous rocks. This is followed at slightly higher pressures by a different facies called prehnite pumpelite facies, originally described from New Zealand. This particular facies is characterized by the presence of calcium aluminium silicates like prehnite and pumpelite in mafic igneous rocks. The upper PT regime of prehnite pumpelite facies is usually ascribed to be 300 degrees Celsius and 5 kilobars. So, it is equivalent to a very low green schist facies temperature that we are dealing with, but at a higher pressure, in line with our idea that we are discussing high pressure metamorphic facies series. Next comes at a slightly higher pressure is what is known as Blueschist facies. Now, why do I call it a blue schist? Because it is blue in color. Now, what gives that blue color? This is an amphibole, which is a sodic amphibole called glaucophane. There are other sodic amphiboles in the amphibole group of minerals like crossite, which is not diagnostic of blueschist facies. The characteristic minerals in the blueschist facies of mafic igneous rocks are glaucophane and lawsonite. These are the two very important minerals they are present, and the blue color is given by this sodic amphibole glaucophane. At slightly higher pressures, we enter into the eclogite facies. Now, the term eclogite was originally coined to designate mafic igneous rocks in the eclogite facies. And a true eclogite by name implies a mafic igneous rocks, although the eclogite facies covers a wider temperature range, but all at high pressures. Eclogite typically contains, the mafic eclogites typically contains the minerals like omphacite and pyrope-rich garnet. Now, what is omphacite? Omphacite is a clinopyroxene. It's a sodium-bearing clinopyroxene, which is a solid solution between diopside, jadeite and acmite. So, it's a very complicated solid solution, I must say, and we are still not clear about the mineral reaction which gives rise to omphacite. But what is very important is that you do not get any plagioclase now in the eclogite. Plagioclase has vanished. Now, how did plagioclase could vanish? Because of breakdown to different minerals, like albite breaks down to jadeite and quartz, anorthite breaks down to grossular, kyanite and quartz. So, in eclogites you sometimes get kyanites as well. So, this sounds a little bit surprising. Kyanite is an aluminous mineral, very common in pellitic rocks, but you do get sometimes kyanite bearing eclogites. You can still metamorphose a rock at higher pressures, but we will deal it separately, not in this module. We will discuss separately extreme temperature and extreme pressure metamorphism, where I will talk about the further conversions in mafic granulites. Now, let us focus to the calcareous rocks now. By calcareous rocks, the name limestone comes to your mind, I suppose. It's so common. But here, I don't mean only limestone. I mean any calcareous rocks. As a general case, I will take a siliceous impure dolomite. But if you have a limestone which contains pure calcite, then metamorphism will produce marble, which is of course a very important and an expensive stone used extensively for flooring and other things. So, what will be the difference between limestone and marble? Nothing in mineralogy, both contains calcite, but if you look under the microscope and see the texture of the rocks, you will see sedimentary textures in limestone and a metamorphic texture in marble. That is the difference. So, the most important aspect of metamorphism of calcareous rocks is that most of the mineral reactions involve a mixed fluid phase, that is to say mostly water and carbon dioxide. Now, what is the complication if we have a mixed fluid phase? It has a complication because partial pressure of water is not equal to the total pressure of fluid, and therefore, we induce an additional variable to be considered here. this is not to say that in no other rock we have mixed fluid. We do have, but we can ignore in many cases, but we cannot ignore in case of calcareous rocks. You will see that the mineral reactions are dependent on not only on pressure, temperature, bulk composition of the solids, but also on the composition of the fluids. And this makes the situation quite difficult. And our phase diagrams are therefore very difficult to draw, because we cannot draw a PT diagram for most of the calcareous rocks. Instead, what we do, we construct isobaric, that is, we keep the pressure constant and change the temperature and composition of the metamorphic fluids. So, you will mostly encounter isobaric TXCO2 or TXH2O diagrams in case of calcareous rocks. I produce two such diagrams in figure 14.14a and 14b. 14a is actually a diagram constructed at 1 kilobar total pressure fixed in the system CaO, MgO, SiO2, CO2 and H2O. The same phase diagram is computed at 5 kilobar in 14b, and you can see that all the mineral reactions are shifted to higher temperatures because of increase in pressure. So, we cannot actually show PTXCO2 variation in one diagram, because we will need a 3-dimension space which will be difficult to decipher. So, instead we normally do like isobaric TXCO2 diagrams to depict phase relations. This system CaO, MgO, SiO2, CO2, H2O actually represents an impure siliceous dolomite in nature. If I metamorphose these rocks at higher in the green schist facies, we get usually the minerals like talc, tremolite, calcite, dolomite, sometimes quartz. And talc is preferred at higher H2O, otherwise talc does not appear, but tremolite is very common. So, you see one fundamental difference. We are getting an amphibole at the very beginning of metamorphism here, which is tremolite, a calcium magnesium amphibole. And subsequently in the amphibolite facies, clinopyroxene, mainly diopside, makes its appearance in such a rock. So, here you are getting a clinopyroxene in the amphibolite facies, and you remember that you got a clinopyroxene in the granulite facies in case of mafic igneous rocks. So, see the diversity, and you must understand the importance of the variation in bulk composition. The common mineral assemblage in amphibolite facies should be diopside. Tremolite a little bit may continue. You can have dolomite, you can have calcite, and you can even have forsterite in a silica deficient bulk composition. You may recall that forsterite is the magnesian olivine. And this is one case where an exception occurs. You can get forsterite coexisting with quartz in such situations. At the transition to granulite facies, elastonite makes its appearance, and you might recall what is elastonite. It is calcium silicate. It is a pyroxenoid crystallizing in the triclinic system. This pyroxenoid makes its appearance at the transition to granulite facies. And in the granulite facies, you get the typical assemblage of elastonite, scapolite, grandite garnet, and you may still get some calcite and quartz, and plagioclase feldspar. And this plagioclase feldspar should be quite calcic in nature because of the bulk composition that we chose to describe. Now, scapolite is a mineral. It's not a mineral, it's actually a group of minerals having different end members of meonite, marialite, etc. And we do get here meonite-rich scapolite, that is calcium-rich scapolite in such metamorphic occurrences in the granulite facies. And we have three reactions, only three in case of calcareous rocks, which are not dependent on fluid composition. And these three reactions can be plotted in PT space. I will describe these reactions when we talk about the very high temperature metamorphism of calcareous rocks separately. Now, what is grandite garnet that I just talked about? Grandite garnet is a solid solution between grossular and andradite garnet, and you do get very peculiar garnets in skarn deposits. Skarn deposits are formed when granitic magma interacts with calcareous rocks and when the system becomes open. So, we have not strictly metamorphism, but metasomatism, or one can say open system metamorphism in this particular case. So, that is the situation in calcareous rocks that we do get in the granulite facies assemblages like garnet, scapolite, olastonite, plagioclase, calcite and quartz. Now, this garnet is unlikely to be almandine bearing garnet unless there was lot of iron in the impure siliceous dolomite. You should expect a garnet rich in grossular or slightly andradite, that is to say grandite garnet. Now, this is the situation with the calcareous rocks. Now, the third component of this module is the ultramafic rocks. Now, as you know, ultramafic rocks occur much less abundantly than the other two rock types. And so, what happened is that they are the least studied also. So, I do not have much to say about ultramafic rocks other than the fact that you recall that by ultramafic rocks we mean magnesium rich olivine, magnesium rich pyroxenes, and perhaps in some cases with calcic plagioclase. This was the original ultramafic rock which we call peridotite, or extreme cases dunite, which is a nearly monomineralic magnesium olivine. Now, these ultramafic rocks, when they get metamorphosed in the low green schist facies conditions, they develop minerals like bluesite, antigorite, which are mostly in the system of MgO, H2O. Now, I have given you a diagram in the system MgO, CO2, H2O in figure 14.15, where you can see that how the mineral assemblages change with progressive metamorphism. So, this bluesite, anticorite kind of minerals in the green schist facies give way to talc and anthophyllite minerals in the amphibolite facies. And finally, we get once again the pyroxenes by decomposition of talc and anthophyllite. Anthophyllite breaks down to enstatite, and then clinopyroxene appears through breakdown of other calcium, magnesium bearing minerals. So, in the final stage in the granulite facies, ultramafic rocks will contain once again two pyroxene bearing assemblages. That is the characteristics of ultramafic rocks. So, in summary, we learned quite a lot of things in this module, in particular about the mixed fluid variable. This is something very unique to calcareous rocks, and you have seen how the composition of the fluid controls the mineral assemblages. just move from left to right in the diagrams in figure 14.14a and b, just if you move from left to right, that is why you are changing the fluid composition only, you will see how much change occurs. We also learned in case of basic igneous rocks or mafic igneous rocks the importance of high pressure metamorphism, and we did not discuss much about ultramafic rocks because we do not have much data on these things, but I do hope that you enjoyed this presentation and it was helpful. Thank you very much.